Hello and welcome to our PEEC2 grant poster presentation where we cover creating a digital thermometer with an Arduino. Joining me in this presentation is Victoria Kaaihili, Pau Isidore Casinto, Eric McIntyre Lewicke, Alexander Smith, and me, Ian Flug. Our mentors were Noah Franco, Guillermo Martin, and our advisor was Dr. Jung Park. So we included an abstract at the beginning of this presentation just to show some relevance and give reasoning as to why we chose what we chose for this project, that being a digital thermometer. And really the reason why we chose to do this generally was because of the whole situation going on with COVID-19 that first appeared in early February of 2020, and as we know, still very much relevant with the second wave. Cases are still being reported all over the country, and one of the key symptoms or key factors into determining whether somebody has COVID-19 or not is if they have a fever. And a very effective way to see if someone has a fever or not is through the use of a thermometer, such as at TSA checkpoints, grocery stores, and other places. And this project, we're really just going to describe what a simple digital thermometer is and how we created our simple digital thermometer. Essentially, what's going to go on is that the thermistor in our circuit is going to capture the temperature readings of its ambient environment through the use of different voltage outputs. And our Arduino, our microcontroller, is going to read these different voltage value outputs and essentially just convert them into temperature values, which we'll show later in our code. When applied heat, the temperature changed on our LCD screen, and really this just kind of showed that our digital thermometer was a success. And we'll go more over the key details of this later.
Introduction and background. Because of the ongoing COVID-19 outbreak, the use of thermometers have become essential. The motive for this project is to create a more accurate and provide a quick temperature readings than the traditional mercury thermometer. This project will produce a thermometer that can provide readings in Kelvin, Celsius, or Fahrenheit. This will become possible with the use of a microcontroller that will run on a specific program and is dedicated in governing the digital thermometer. We will be using an Arduino Uno to serve as a microcontroller. Thanks to Arduino Uno, we can control the functions of our board by uploading a set of codes, which Ian, my fellow participant, will go in detail in the upcoming slides. We must also remember that before we upload the code, it is required to install the Liquid Crystal library, otherwise the code won't work. And finally, the key component for the thermometer is the thermistor. A thermistor is a resistor whose resistance is dependent to temperature. Now, there are two types of thermistor, an NTC or negative temperature coefficient and PTC or positive temperature coefficient. In this circuit, we will be using an NTC thermistor, which is a resistor whose resistance decreases as the temperature increases.
Aloha, my name is Alika and I'll be covering the methodology portion for this segment. Our first step was to draft the circuit board, and we used the Eagle program to do so. We sent over the schematics after we were done to a mainland company called Osh Park for manufacturing. And while we were waiting for them to return our circuit boards to us, we drafted up cases for our microcontrollers using SolidWorks and later a 3D printer to print them at school. Once this was accomplished, we took all the required pieces and soldered them in order to set up our microcontroller. Once we were done with this, we used a code using our Arduino program. We were able to effectively display the temperature as desired, whether Celsius, Fahrenheit, or Kelvin. Now, when fully functional, the thermometer runs off a 5-volt power source that sends current through a 10K resistor and then to the thermistor. The thermistor then takes the reading from its sensor and sends that signal to the microcontroller, which then sends the signal to the LCD screen in 3 different formats depending on what we change the code for. We also added a potentiometer that we may be able to adjust the screen brightness with.
So just to kind of go over the code real quick and a little more in depth, what you're really seeing here is the pin connections and the establishment of the pins between the Arduino and the LCD. And the middle section essentially is just all the math that converts the voltage data from the thermistor into Celsius, Fahrenheit, and Kelvin. And on the bottom essentially is just the layout, the formatting for how the information will be displayed on the LCD. And below you have the delay 500, which means that this just kind of refreshes every half a second. Moving on from the code slide real quick, we're just going to kind of go over the PCB design layout. What you're seeing in blue here, those are just the laser tracings made, the metal connections that will be made to each component. And in green, what you're seeing here, these are just the pads, and we custom edited the pad diameters as well as the hole diameters so that there's enough surface area for soldering as well as the proper fitment for each of the different components. Now what you're seeing in gray, this is called a silkscreen layer, and essentially what it is it's just labeling on the top of the PCB board. And you have the layouts for each of the components as well as our names. We use PAL as an example here, and what our PCB is, a thermometer. And what you're seeing in D12, D11, and so on, those are just the connections to be made to the Arduino. Here we're just going to kind of go over our final product again in a bigger picture, just a little more in depth to point out the key components. As you can see at the top, we have our LCD screen, and we have our jumper wires going to our PCB board, which contains our 10K potentiometer with the black knob, our thermistor, which looks like a little black bulb, which is right next to our small blue 10K resistor, and we have our other jumper wires that go from the PCB board to our Arduino Uno, our microcontroller, and this is to kind of show you our overall setup.
Flow of control. A voltage divider is a simple circuit which turns a large voltage into a smaller one. By using just 2 resistors and an input voltage, we can create an output voltage that is a fraction of the input. Using a thermistor and a resistor, we created a temperature-related voltage divider. The Arduino will measure the voltage and translate the temperature. First, the temperature-related output voltage from the voltage divider is recorded and sent to the Arduino. The voltage input and output is plugged into a formula to find the thermistor resistance. Once the thermistor resistance is calculated, it is then plugged into the Steinhardt formula to translate the data into a temperature of Kelvin units. Depending on your need, you can adjust the code for the Arduino to go a step further and convert Kelvin into degrees Celsius or degrees Fahrenheit. Once the temperature is calculated, it is then displayed on the LCD screen. This process is repeated at every half of a second.
The result of our product was a thermistor that was accurately able to record a temperature, display it on our LCD, and show an increase or decrease in nearby ambient temperatures. The LCD screen was also capable of reading temperatures in both Celsius and Fahrenheit. Looking at the below image, you can see that our thermometer is accurate all the way to a 1/100th of a degree and is capable of recording rapid changes in the local environment. In the future, if we wish to improve upon our sensor, the first thing we would work on is reducing power consumption of the thermometer. We would also add additional sensors to help with the accuracy of the device, such as infrared, smoke detection, and a light detector. Also, if you wish to make this thermometer accessible to a wide audience, we need to lower the cost of our digital thermometer, allowing schools and other members of the community easy access to this device. Finally, due to complications with our 3D printer and the ongoing COVID crisis, we were unable to create a case for our device using SolidWorks, so this would be another essential part of our product. This summer bridge program was provided by the Pre-Engineering Education Collaborative, or PEEC, funded by the National Science Foundation. We thank our mentors Noah Franco and Guillermo Martin for guiding us through the program. We would also like to thank Eligo for providing their Super Starter Kit for Uno, which gave us the tools necessary to create our thermometer.